Welcome! In this video, we'll be solving LeetCode problem number 1378, replace the substring for balanced string. This is an interesting problem that challenges us to find the smallest substring we can replace to balance a given string of characters. We'll break this down step by step and explore the most efficient solution. Let's get started. In this problem, we are tasked with balancing a string that consists of the characters Q, W, E, and R. A string is considered balanced when each of these characters appears an equal number of times. If the length of the string is n, then each character must appear exactly n/4 times for the string to be balanced. To achieve this balance, we are allowed to replace at most one contiguous substring of the string with another substring of the same length. Our goal is to determine the minimum length of the substring that needs to be replaced in order to make the string balanced. The input is a single string s of length between 1 and 100,000, and the output is a single integer representing the minimum length of the substring to replace. Let's take a look at some examples to better understand the problem. In the first example, the input string is s equals QWER. Here, the string is already balanced because each character Q, W, E, and R appears exactly once, which matches the requirement for n/4 when n equals 4. Since no replacement is needed, the output is 0. In the second example, the input is s equals QQWE. This time, the string is not balanced because Q appears twice, while the other characters appear only once. To balance the string, we can replace one Q in the substring QQW with an E, making all character counts equal. The minimum length of the substring to replace is 1, so the output is 1. Now, consider the third example, where the input string is s equals QQQW. In this case, Q appears 3 times, while W appears only once. To balance the string, we need to replace two Q's in the substring QQQ with E and R, resulting in the balanced string QWER. The minimum length of the substring to replace is 2. In the fourth example, the input string is s equals QQQQ. Here, all 4 characters are Q, so the string is highly imbalanced. To balance it, we need to replace 3 Q's with W, E, and R, creating the balanced string QWER. The minimum length of the substring to replace in this case is 3. Finally, we should note the constraints and additional considerations for solving this problem. The length of the string s can be as large as 100,000, and it consists only of the characters Q, W, E, and R. A balanced string is defined as having each character appear exactly n/4 times, where n is the length of the string. To solve this problem efficiently, we can use a sliding window approach to find the smallest substring that, when replaced, balances the string. It's important to handle edge cases, such as strings that are already balanced, strings that are highly imbalanced, and very short strings. These examples and constraints provide a clear roadmap for implementing the solution. To solve problem number 1378, the goal is to determine the minimum length of a contiguous substring that can be replaced to make the string balanced. A string is balanced when each of the 4 characters Q, W, E, R appear exactly n/4 times, where n is the total length of the string. While this might seem straightforward at first glance, a naive approach would involve replacing every possible substring and checking if the resulting string is balanced. This brute force method requires iterating through all possible substrings, replacing them, and verifying the balance condition by counting the character frequencies. However, this approach has a high computational cost. Generating all substrings alone takes n squared, and verifying each substring adds another n, making the total complexity n cubed. For large strings, where n can reach up to 100,000, this becomes impractical due to the sheer number of operations required. Thus, we need a more efficient strategy. A better solution is the optimized sliding window approach. The key intuition here is that instead of replacing substrings blindly, we can systematically use a window to find the shortest substring that, when replaced, eliminates the excess characters causing the imbalance. There are 2 important observations to note. First, the string is balanced if the frequency of each character doesn't exceed n/4. Second, any character exceeding n/4 contributes to the imbalance. By pre-computing the excess frequencies for each character, the problem reduces to finding the smallest substring that removes these excesses. The steps for this method are straightforward. First, calculate n/4 for each character. Then determine the excess frequency of any character exceeding this threshold. Finally, use a sliding window to identify the smallest substring that eliminates these excesses. The window expands by moving the right pointer and shrinks by moving the left pointer, ensuring the balance condition is satisfied. This approach processes each character at most twice, leading to a time complexity of O(n), which is far more efficient than brute force. An alternative two-pointer approach achieves the same result, dynamically adjusting the substring boundaries without explicitly maintaining a window. However, its complexity is identical to sliding window at O(n). The optimized sliding window approach is the chosen solution, as it is both time-efficient and space-efficient. With O(n), time complexity, and O(1), space usage, it avoids the inefficiencies of the brute force method while remaining intuitive and scalable. The breakthrough insight here is recognizing that the problem boils down to finding the smallest substring whose removal balances the excess frequencies. This eliminates the need to generate or test every possible substring, making the solution highly practical for large inputs. In comparison, the brute force approach, while conceptually simple, is computationally prohibitive with O(n)³ complexity, making it unsuitable for larger values of n. On the other hand, the sliding window method strikes the perfect balance by leveraging key observations to achieve optimal performance. The two-pointer alternative, while functionally equivalent to sliding window, may be less intuitive for some due to its implementation style. Ultimately, the sliding window approach stands out for its clarity, efficiency, and scalability, making it the ideal solution for this problem. In this problem, we want to determine the minimum length of a substring that can be replaced in order to make the given string balanced. A string is considered balanced when each of the four characters Q, W, E, and R occurs exactly n/4 times, where n is the total length of the string. The challenge lies in identifying and replacing the smallest possible substring to achieve this balance. To solve this efficiently, we use a sliding window approach. Instead of testing every possible substring, which would be computationally expensive, the sliding window dynamically adjusts its size while ensuring the balance condition is met. A frequency map is essential here. It allows us to track the occurrences of characters outside the window and check if the current substring satisfies the balance condition. This combination of techniques ensures we can efficiently find the optimal solution. The sliding window technique is particularly powerful for this problem because it ensures we only process each character once, resulting in an efficient O(n) runtime. To implement this, we rely on two key data structures. The first is a frequency map, which keeps track of the count of each character outside the current window. This map is crucial for determining whether the current window satisfies the balance condition or not. The second is the sliding window pointers, left and right, which define the boundaries of the substring we are considering. By adjusting these pointers, we can expand or shrink the window dynamically, making it possible to explore all potential substrings without redundant computations. To implement the algorithm, we start by initializing a few variables. First, compute the target frequency, which is n/4, as this represents the maximum allowable count for each character. Next, create a frequency map to count the occurrences of each character in the string. We also initialize sliding window pointers left and right to 0, and set min_length to n, which will store the smallest window size that satisfies the balance condition. The algorithm then iterates through the string using the right pointer to expand the window. For every character at s, right, we decrement its count in the frequency map, as it is now part of the window. After expanding the window, we check whether the remaining characters outside the window meet the balance condition. If they do, we update min_length with the current window size. Finally, to optimize further, we move the left pointer to shrink the window while ensuring the balance condition is still satisfied. This allows us to refine the result and find the smallest valid window. Once all possible windows have been processed, we return min_length, which represents the minimum length of the substring that needs to be replaced to achieve balance. There are a few edge cases to consider. If the string is already balanced, the result is 0 because no replacements are needed. If all characters in the string are the same, for example, QQQQ, the result would be n/4, since we need to replace all but n/4 instances of the character. For strings with uneven distributions of Q, W, E, and R, the sliding window dynamically adjusts to find the optimal solution. In terms of complexity, the algorithm is efficient. The sliding window ensures each character is processed at most twice, once during expansion and once during shrinking, resulting in a time complexity of O(n). The space complexity is O(1), because the frequency map only tracks the fixed set of 4 characters. Let's walk through an example to solidify our understanding. Consider the input string WQWRQQQW. The target frequency is lens/4, which equals 2. Initially, the frequency map shows Q occurs 4 times, W 2 times, R once, and E not at all. Using the sliding window, we start with left at 0 and expand right. At right equals 4, the substring WQWR satisfies the balance condition, so we update min_length to 4. Next, we shrink the window by moving left while maintaining the balance condition. At right equals 6 and left equals 3, the substring RQQQ still satisfies the condition, and we update min_length to 3. After processing all possible windows, we return min_length equals 3 as the result. This example demonstrates how the sliding window efficiently identifies the optimal substring for replacement. To solve the replace the substring for balanced string problem, we begin by importing the counter class from the collections module. This will help us count the frequency of each character in the string efficiently. Inside the solution class, the function balanced string takes the input string s. The variable n holds the length of the string, and target calculates the ideal frequency for each character, which is the total length divided by 4 since we want the string to be balanced with equal counts of Q, W, E, and R. Next, we use the counter class to count the frequency of each character in the string s and store it in char_count. Then, we check if the string is already balanced by verifying that the count of each character does not exceed the target. If this condition is met, we immediately return 0 since no replacement is needed. If the string is unbalanced, we initialize 2 variables, left, which will track the start of the sliding window, and min_length, which will store the length of the smallest substring that can be replaced to balance the string. The sliding window approach is then used to iterate through the string and dynamically adjust the counts of characters within the window. As we iterate through the string, the right pointer expands the window by moving 1 character at a time. Each time a character is added to the window, we decrement its count in char_count. Now, we check if the current window satisfies the balance condition by ensuring that all character counts in char_count are less than or equal to the target. If it does, we calculate the length of the current window and update min_length if this length is smaller than the previous minimum. Then, we shrink the window by incrementing the left pointer and restoring the count of the character at that position. This process continues until we have examined all possible windows. Finally, when all iterations are complete, we return min_length, which represents the length of the smallest substring that can be replaced to make the string balanced. Here, we begin by importing the necessary packages and defining our solution class. The method balanced string takes a string s as input and aims to determine the minimum length of a substring that can be replaced to make the string balanced. First, we calculate the target frequency for each character, which is the total length of the string divided by 4, since the goal is to have equal counts of Q, W, E, and R. Next, we use a hash map to count the frequency of each character in the string. If the string is already balanced, we return 0 immediately. Otherwise, we initialize 2 pointers, left and right, to implement a sliding window approach. The variable min_length is used to track the shortest substring length that meets the balancing condition. As we iterate through the string, we decrement the frequency of the character at the right pointer and check if the current window satisfies the balance condition using the helper method isBalanced. If the balance condition is satisfied, we update the min_length by comparing it with the size of the current window. Then, we increment the left pointer to shrink the window from the left, while restoring the frequency of the character at the left pointer. This process continues until we exhaust all possible windows in the string. Finally, we return the min_length, which represents the shortest substring that needs to be replaced to achieve balance. The helper method isBalanced checks whether the frequency of any character exceeds the target. It iterates through each of the 4 characters Q, W, E, and R and ensures that none of their counts exceed the target. If all conditions are met, the method returns true, indicating that the current window is balanced. Otherwise, it returns false. This approach efficiently combines sliding window and frequency counting to solve the problem within optimal time complexity. To start off with example 1, we are given the input string s equals qwer. The length of the string is n equals 4, and the target count for each character to achieve balance is calculated as n/4 equals 1. Using this, a frequency count of the string shows each character q, w, e, and r appears exactly once. Since all character counts are less than or equal to the target of 1, the string is already balanced. Therefore, no replacement is needed, and we simply return 0 as the result. Now, in example 2 with the input s equals qqwe, the setup is similar. The length of the string is n equals 4, and the target count for each character is again 1. However, this time the frequency count reveals that q appears 2 times, while w and e appear once each. This means the string is not initially balanced. We begin a sliding window approach starting with both the left and right pointers at the beginning of the string. By decreasing the count of q at the right pointer, the updated counts become q1, w1, e1. Checking the balance condition, we see that all counts are now within the target. At this point, we calculate the window length, which is 1, and update the minimum replacement length to 1. Afterward, we restore the count of q and move the left pointer forward to continue the process. With the left pointer now at position 1 and the right pointer still at position 1, we reduce the count of q again, resulting in updated counts of q1, w1, e1. The balance condition is satisfied once more, so we verify that the window length remains 1 and update the minimum replacement length accordingly. After this, the count of q is restored, and the left pointer is advanced to position 2. At this point, the sliding window process concludes because all possibilities have been checked. The minimum length of the substring that needs to be replaced is 1, which we return as the result. For example 3, the input string is s equals qqw. Here, the length is still n equals 4, and the target for each character is 1. The frequency count shows that q appears 3 times, while w appears once. Since q exceeds the target, the string is unbalanced. We begin the sliding window with both pointers at position 0. Reducing the count of q gives us updated counts of q2, w1, but the balance condition is not yet met because q still exceeds the target. Next, we expand the window by moving the right pointer to position 1 and decreasing the count of q again. Now the counts are q1, w1, satisfying the balance condition. The window length is 2, so we update the minimum replacement length to 2. After restoring the count of q, the left pointer advances to position 1. With the left pointer at position 1 and the right pointer at position 2, we reduce the count of q once more, resulting in q1, w1. The balance condition is still satisfied, and the window length remains 2. The minimum replacement length is kept at 2. After restoring the count of q, the left pointer moves to position 2, and the sliding window process ends. The smallest substring length that needs to be replaced to balance the string is 2, which we return as the final result. In analyzing the time complexity of this algorithm, we start by considering the sliding window approach combined with frequency counting. The first step involves calculating the frequency of each character in the string using the counter function. Since the function iterates over the entire string once, this step takes n time, where n is the length of the string. Next, we have the outer loop, which iterates through each index in the string using the right pointer. This loop executes exactly n times, contributing another n to the time complexity. Within the outer loop is the inner while loop that adjusts the left pointer to shrink the window as needed. The key insight here is that the left pointer traverses the string at most once across all iterations of the right pointer. This means each character is processed at most twice, once when expanding the window and once when shrinking it. As a result, the total work done by the inner loop also sums to n. Now, let's examine the balance condition check. This step uses the all function to ensure that the frequency of each character remains within the allowable limit, defined by the target. Since there are only 4 unique characters in the string q, w, e, and r, this check involves just 4 comparisons, making it an O1 operation. Combining all these steps, we arrive at a time complexity of n for the initial frequency count, n for the outer loop, and n asterisk O 1 for the inner loop and balance checks. Altogether, this simplifies to O n as the dominant term. Shifting to space complexity, the primary contributor is the counter object, which stores the frequency of the 4 unique characters. Since the number of characters is constant, the space required by the counter is O1. Additionally, the algorithm uses a few integer variables and simple data structures, which also require constant space. Therefore, the overall space complexity remains O1. Since no additional data structures beyond the frequency counter and a few pointers are used, the space requirements do not grow with the size of the input. This solidifies the overall space complexity at O1. Now, if we compare this sliding window approach to a naive solution, the differences in efficiency become clear. A brute force method would involve generating all possible substrings and checking if replacing each substring results in a balanced string. Generating all substrings alone would take O n squared time, and verifying the balance condition for each substring adds another O n, leading to an overall time complexity of O n cubed. In contrast, the optimized sliding window approach avoids this inefficiency by dynamically maintaining a valid window and using frequency counts to verify the balance condition in linear time. With a time complexity of O n and space complexity of O1, the sliding window approach is vastly more efficient. Looking at the best, average, and worst cases for this algorithm, we find that the best case scenario occurs when the string is already balanced. Here, the all check immediately confirms the balance condition after the initial frequency count, allowing the algorithm to terminate early with a time complexity of O n. In average and worst case scenarios, the algorithm needs to adjust both the right and left pointers across the entire string to maintain the dynamic window. Even in these cases, the time complexity remains O n, because each pointer processes each character at most once. To confirm this mathematically, the outer loop runs O n times, and the inner loop processes every character at most once, resulting in O n work overall. The balance condition checks are O1 per call, which does not affect the dominant term. Thus, the total time complexity is O n, and the space complexity is O1, making this algorithm both time and space efficient. When tackling this problem, there are several common mistakes that can trip you up if you're not careful. First, failing to handle all edge cases can lead to incorrect outputs. For example, if the string is already balanced, some solutions mistakenly return a non-zero substring length because they don't check the initial state of the string. Always validate whether the string is balanced before attempting any replacements. Second, it's easy to mismanage updates to the sliding window, particularly with the left pointer. Moving it too soon or failing to update it correctly can result in invalid substring calculations. Make sure both pointers are adjusted based on frequency constraints. Lastly, overlooking efficient frequency calculations can cause performance bottlenecks. Instead of recalculating counts for every window, use a hash map or frequency array to maintain dynamic counts, which will save significant computation time and prevent time limit exceeded errors. Another common pitfall is misunderstanding the definition of a balanced string. Remember, a string is considered balanced only when each character appears exactly len/4 times. Misinterpreting this definition can lead to solving the wrong problem entirely, so take the time to clarify and validate this concept early on. Additionally, for larger inputs, it's crucial to optimize your solution. A naive approach that doesn't use techniques like sliding windows will likely result in O n squared complexity, which becomes impractical for larger constraints. Always consider the input size and make sure your approach is efficient enough to handle it within the given limits. When preparing for interviews, it's essential to have a strong grasp of the sliding window technique because it's a key part of solving this problem efficiently. You should be able to explain how and why the window expands and contracts based on character frequency constraints. Interviewers are also likely to test your ability to handle edge cases, such as strings that are already balanced or those with just one unbalanced character. Testing these scenarios during your implementation will help you avoid surprises. Furthermore, articulate your thought process clearly, particularly when explaining why the sliding window is more optimal than brute force. Highlight the role of maintaining a dynamic frequency count, which reduces the complexity from O n squared to O n. Lastly, practicing related problems like longest substring without repeating characters or minimum window substring can help reinforce these concepts and prepare you for similar challenges. There are also alternative approaches to consider, each with its own trade-offs. The brute force approach involves generating all possible substrings, replacing them, and then checking if the resulting string is balanced. While straightforward, this method is highly inefficient with a time complexity of O(n cubed, making it unsuitable for larger inputs. A more efficient method is the frequency-based sliding window. By maintaining a dynamic substring and calculating whether replacing it balances the string, this approach achieves optimal performance with O(n) complexity. However, careful implementation is required to handle edge cases correctly. Another option is combining binary search with the sliding window. Here, you use binary search to find the minimum substring length that can be replaced to balance the string. This method is slightly more complex but can be useful in scenarios with additional constraints. Each method has its place, but for most cases, the sliding window approach is the most practical and efficient. Great work! To summarize, we tackled LeetCode problem number 1378 using an efficient sliding window approach with O(n) time complexity. Key takeaways include the importance of using sliding windows for substring problems and analyzing frequency distributions for balance constraints. If you enjoyed this session, don't forget to like, subscribe, and stay tuned for more problem-solving techniques. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!